All right. Good morning, everyone. I think we have taken our due time to get started, so let's just get started. Um, so today in this session, we'll be talking about scaling row-level deletions. I'll talk about in general the trend in the industry, but very specifically, I'll focus on how we do that at Pinterest. Um, Here's our short and sweet agenda. And data world, you can't talk about scaling things unless you prove your credibility. And in data, we prove our credibility by talking about scale at which we operate. So we'll start with talking about data scale at Pinterest. I'll then talk about table format evolution that we went through at Pinterest, and it also aligns with like what we have seen in the industry. Row-level data deletion is where we'll be spending most of our time today. And towards the end, definitely, there will be ample opportunity for you all to ask any questions. But first, let's talk about the most important thing, which is about me. I'm Ashish Singh. I'm a senior technical leader at Pinterest. I work on things related to big data query processing, data formats, table formats. I am also an Apache committer and have been contributing to various Apache projects like Parquet, Iceberg, Kafka. In the past, I have also contributed to Hive and Apache Sentry. Okay, so as I promised, let's talk about or look at how the data scale at Pinterest looks like. We operate at a exabyte plus data in AWS S3, and we have 150,000 data compute jobs that run every day. And these doesn't include any metadata operations. We have over 20,000 Hadoop nodes, over 1,000 Presto workers. We have over 300,000 Hive tables. We are not proud of saying that. We're trying to cut it down as much as we can. And everything is on cloud. So for data storage, we have S3. For compute, we use EC2 machines. Now, when I say we are going to talk about data deletion in Pinterest, it doesn't mean we run all of these exabyte data through deletion. That will be a crazy big number. Okay, so let's look at how table format evolved in industry and how that I'll also try to tie that in with like what we saw at Pinterest. Until 2019, Hive was the dominant Hive table format. We all know, we all likely still use it. But in starting 2019, we started seeing that there are alternate table formats like Hoodie, Iceberg, Delta. They started taking traction, getting a lot of attention. And at Pinterest, it was after 2020 when we started getting serious about these alternate table formats. And the reason for which we started doing that, I'll be talking about that in the next slide, but yeah, it was between 2020 and 2022, we did a lot of evaluation on what table format we should choose, built out the integrations with our systems, and then in 2022, we went live with Apache Iceberg as the table format that we support at Pinterest. In addition to Hive table format, we still have a lot of Hive tables. Fast forwarding to today, we have more than 50% of all of our data deletion use cases powered by Iceberg. And we are hoping to move entire data deletion use case on Iceberg pretty soon. So as I said, in 2020, we started looking into alternate table formats. For us, the reason for that was essentially among three dimensions. The first was the general job reliability, performance, and efficiency. As I said, all of our data was on S3. It's still on S3. And for our compute jobs, like just to do a job planning, we would go list a prefix, and that will take ages. We'll see 503s. So even before we start doing interesting work, the job planning, we were seeing a lot of slowness. In some cases, some of the very large prefixes can take up to like 30 minutes. And all those list calls, they add up and quite a bit of cost us quite a bit of money too. The other issue was because we are just relying on S3 for the current state of the data set, There were scenarios where the jobs would just fail, and that was one of the other issues that was hitting our reliability pretty hard. The second dimension is mostly around version data set. With Hive, and if you have your data stored on object store like S3, your data can be directly accessed outside of your table definitions. So with that, what can happen is, for example, if you are running a backfill, you are overriding your live data, right? And that would mean any concurrent reads or writes happening would get affected. So for us, like providing a consistent view of data was getting more and more important as we were seeing that the backfills are getting more expensive and more troublesome. And that is where we really have to be reliable so that we can get out of incidents very quickly. The third dimension was essentially around setting up our future needs. So we wanted capabilities like write, audit, publish. We wanted better data quality checks. We wanted to be able to change the partitioning layout without rewriting all the data of a Hive table. We wanted to do time travel. Not we, but our users wanted to do all these things. And then in the past, these things were not a requirement, but then people are building expectations that these like row level mutation doing time travel will be possible on big data data sets as well. Okay, so now we'll be talking about the meaty stuff, row level data deletions. So at Pinterest, there was primarily two reasons for us to look into row level data deletions. One was compliance, and I'm sure I'm not alone when I say this. For Pinterest specifically, we had to honor the user data deletion request and also the advertiser data deletion request. The other suite of use cases were mostly around trust and safety, where we wanted to remove historic activities of a spammer. And there are traditionally two ways of doing row-level deletions. This is like pre-Iceberg and Delta and Hoodie era, where all you need to do is you have to read the file that has the data you need to delete. You delete the original file. In memory, you do the filtering of the data, and then you write it back to the original location, which works fine, except if there are concurrent reads and writes going on. For example, a user came in, they started their job. The job went in, did the listing of the prefix, planned the job, planned out all the tasks, and then started executing. Meanwhile, there was a deletion happening, right? So it actually deleted the original file. In that case, the user's job will fail because the original file doesn't exist anymore. And this is one of the reasons, main issues that Iceberg can help us fix, and we'll talk about that in a bit. The other paradigm is that you can move all the data access or finding out where is the data behind Metastore thing. So for us, it was mostly Hive Metastore. So where this becomes a central place where a user goes in, tries to figure out, oh, for this particular name of the table, where is my data? And what that allows you to do is you can write the new data, which is the filtered out data, into a separate location and atomically update the partition table pointer or location to this new location. That can help alleviating some of the problems with concurrent reads getting affected when the deletion is going on. And this is exactly what we used to do at Pinterest. We call the system amnesia. And this system came with its own set of issues. The issues ranged from, because with the system, we are scanning all the data, right? That means entire table, all partitions, all rows, all columns, entire data set. And our data sets are in tens of petabytes. It can be very expensive. It reads all the data into memory, does the filtering, and then writes the data back. And this is very expensive for us. And because the amount of computation involved, it was very long job run time. It will take days, and you can assume things will go bad in days. So our reliability of these jobs was pretty low as well. I think this is a good time for me to introduce Iceberg because we'll be talking about how Iceberg is going to help us resolve the issues that I just mentioned. I'm pretty sure most of the folks here know what Iceberg, so I won't go into the details. But for those who don't, Iceberg is a open table format for analytical data sets. The crucial thing about Iceberg that really helps with the data deletion is snapshot. It provides you a consistent view of data set at a given point of time, which is referred to as snapshot. The other thing that's very important is that it provides a hierarchical access to data files. So you have snapshot, you have multiple manifest lists beneath it. Each manifest list has multiple manifest files, and then like they point to the data. And then they are metadata stored at every level that can help you avoid doing things like, oh, first you have to read the file footer to figure out if you even need to read the file. Okay, so now let's specifically talk about how Iceberg, like the general ways of doing deletions with Iceberg. There are essentially two ways to perform a row-level deletion with Iceberg. One is copy on write approach, and the other is merge on read approach. Copy on write is essentially while the deletion is going on, we make the copy of the data, which has the filtered rows, and then you can delete the previous file as well. But most of the work is happening while the deletion is happening. So it will actually do the copy of entire data if there's a need to be. The other approach is merge on read. In this approach, most of the work happens on the read side. So in the delete operation, all it will do, it will just write the delete filters. And on the read side is when it will do the computation, which is essentially merging. While reading, it will filter out the rows that essentially should be deleted. The former, copy on write, is most suited in read-heavy workloads, which is what we have at Pinterest mostly. So for that reason, we went with the copy on write. We are still with copy on write deletions. On the other hand, merge on read is really good for use cases which are write heavy. So for example, if you have a CDC pipeline, which is very write heavy, merge on read will be very beneficial there. Okay, so I talked about snapshot a bit, and I said like that's one of the key reasons why Iceberg helps with the deletion. But to understand that a bit more, in this example here, we have like multiple snapshots of, we can assume it's a data set. And what we see here is that a reader is reading from snapshot S2. And while it's reading, there was a new snapshot written, snapshot 3, or even like snapshot 4 was written. But the reader can continue to read from snapshot 2 for the entirety of its process, unless someone runs a compaction in between, in which case the old snapshot will be gone. But this essentially what we are trying to show here is that concurrent reads and writes can operate without affecting each other, which is one of the key issues we were facing with deletions on the Hive tables. To understand better, I'll walk you through a deletion illustration with Iceberg. So in this case, like what we are looking at is we have a data set, in this case, the data set 1. It has just one snapshot, snapshot 0, manifest list, manifest files, and then you have the actual data files. And for each of the data file, you also have some stats stored in the manifest file itself. Now, say you have a use case where you have to delete a row. For example, say you want to delete a row that matches a particular filter. We can assume that like we want to delete a row where partition 1 is 2, partition 2 is C, and then say like we want to delete a row in data file 6. So say like column 1 is F and column 2 is 50. Now, in this case, the first thing that happens when you run a delete operation using Iceberg is it will first try to find out which files I need to read, right? In this case, based on the filters, it will very easily find out that, oh, there is just one file out of all of these 6 files. Just one file has the data that needs to be deleted. The next step would be, this is what it will do in the job planning phase. The next step it will do is it will write a new file. So it will just read the one file, data file 6. It will generate a new data file 7. And it will definitely update the stats for it. And because data file 7 is a new file, so it will have to create a new manifest file, which points to everything in the previous manifest, which is manifest file 3. Except for the file that is deleted, which is data file 6, and it will replace data file 6 with the data file 7. But it does not actually delete the data. So if someone is still reading from the old snapshot 0, they will still see data file 6 just fine. It's only after you run a compaction or expire snapshot procedure at which point old snapshots, old metadata, and old data files are actually deleted. So great. We talked about, we showed you how Iceberg can limit the number of files that actually needs to be rewritten during a deletion, right? Now, the problem still remains if that Iceberg is still returning you all the files that needs to be rewritten, which can be the case if you have data sets that are very well distributed across all the files. And for example, if you have a system where you have 450 million active users, and they are operating every day, and their data is almost in all the files. Now, if one of those users asks you to perform any deletion, likelihood that their activity is logged in all the files. So Iceberg can't really do anything there. This is what we were seeing. We saw that even though we moved from Hive table deletions to an Iceberg table deletion, the performance improvement that we saw was very minuscule. And the reason was that we were touching all the files. And so essentially we were doing the same amount of work. There was definitely some cost reduction in the job planning and then the commit. But then the meaty part of the work, which is rewriting the files, was still the same. So next, what we did was we utilized sorting. Because if we can, the problem was that we were touching all the files. If we can change the data layout in a way that all the requests from a user can only be processed by touching a few files, that will address our concern that we are rewriting all the files. So to do that, we started changing the data layout by introducing sorting based by user identifiers and then advertiser identifiers, because those are the two identifiers that we mostly did deletion based on. Now, with this, we did see a dramatic decrease, not just in the S3 footprint or our dataset footprint, for obvious reasons, because our data format was in Parquet. So the more similar data are co-located or in the same file, you get a better compression. So for that reason, we have seen compression or the data size reduction up to 50 to 75%. And not just that, it also helps with decreasing the compute cost for downstream jobs. Because say if your downstream job is filtering or grouping by a particular user ID, you get the benefit that you're reading less number of files because the data is already sorted by those IDs. So great. With this, we did saw performance improvement. We saw with the sorting, we were able to reduce the cost by another 20-25%, but definitely at the scale that we were operating on, this wasn't good enough for us. The issue with sorting is that it's very expensive. If you have to sort a 10 petabyte data set, that shuffle stage is going to be super expensive and can induce a lot of failures too. So this is a problem then we started digging into next. We took the advantage of the fact that Iceberg data file holds a lot of metadata about the data file. One of those things that it also keeps in note of is the sort ID. So if a data file is already sorted, we don't need to sort it again. And for us, what we did was we extended that idea to the entire partition. If the partition is already sorted, we don't have to sort it again. We just have to make sure that we are rewriting the entire file as is after deleting what we need to delete. So we essentially, I linked the PR here. It has a bunch of discussion. It's not a generic solution that you can apply to any data set. Sorting and then serves its purpose. But what we did for our specific use case, where we knew the deletion pattern exactly, we knew how we are performing the deletion, so we took advantage of all that information. And essentially, what we do is we turn off the sorting, shuffling, when we see that all the files that needs to be rewritten are already sorted. And the sort ID is same as the table sort ID. So there was no change made in the spec in terms of partitioning or sorting. So with that, what we see is first time we perform deletion, the cost is high. The cost is pretty similar to what we used to see with Hive table based deletion. Because in this first deletion, we sort the data. And all the subsequent deletions, the cost drops significantly. And what we are seeing right now is that the cost has dropped around close to 800%, which is a comfortable place to be in. But then we are now seeing that over a period of time, if you keep doing that, you get into some situations where you have very small files. Maybe a user was very active on a particular day, and so the entire file had just that user and a little bit of activity from a few other users. If you delete that one user, the file becomes small. So the next sort of challenge that we are looking into right now, and so I won't be talking about it, is how do we make the data sets that have went through all these deletions and have the small file issues, how we can optimize the data again to bring down the cost. So yeah, that's pretty much I had on the Iceberg, scaling data deletions with Iceberg. This slide essentially talks about a bunch of OSS contributions Pinterest has made. In the interest of time, I won't be going over the individual details, but I'll be around to answer any questions. And yes, we had a bunch of changes that we keep internal to Pinterest. These are mostly integrating with the internal systems, internal security practices, and all that. Yeah, and with that, I'll open for questions. All right.
Kelly.
Hi, quick question. What is the scale of deletes that you're talking here? And part two is, what is the percentage of delete jobs compared to other workloads, like mostly read workloads, right?
Very good question. So the question is, what is the scale of the deletion data sets that go through deletion? It's still in petabytes of data. I think I can quote that the largest data set that will go through our deletion is around a few petabytes, close to tens of petabytes of data. And we have multiple such. So right now we are around 20, 25 petabytes of data that goes through deletion. By end of this year, we are hoping it to include all the deletion use cases. So that will be much more. The second was,
This is about the percentage of deletes compared to other read operations.
Got it. Yeah. The deletion, we try to keep them as minimal as possible. So depending on how your company decides to handle the compliance, I can't speak of the legal reasons at what frequency we perform the deletions, but then It's not as frequent as like your daily other jobs, right? But the good thing with Iceberg is that because like when we are deleting stuff, we are doing things like making conscious choices, like, oh, what are the sort keys we should be using. The downstream jobs also benefit from that. So what we have seen is that data sets that actually go through deletion are way more performant than the data sets that don't.
Related question. When you say delete data set is roughly in tens of petabytes, right? And total data set is like 25-ish petabytes, right?
Right.
That's a lot of data you're deleting. And when you're talking about row level deletes, I was thinking row level data is much smaller. Are you referring to these 10 bytes as the whole data files getting deleted, or what is this?
Oh, no. This is the entire data size that we process.
Okay.
The amount of data that would delete could be very small.
Okay.
I can't
Sure.
give you the number. I think you. Oh, okay. Cool.
Yeah, so back on Cow and more, what you were talking about, you're mostly
Read heavy.
copy on write, but so then what percentage would you say you do have for read versus write? Are you like 95, 99? I mean, can you comment on that, or?
Yeah, I can comment on that. So we have metrics. I don't remember the exact number, but then I think it's very. So our data is like what? If we write like a couple of petabytes every day, then the reads are still in terms of like hundreds of petabytes every day. There are some reasons that contributes to that factor. First reason that comes to my mind is not all of our data sets are columnar. So what that means is that even if you want to read one column, you would read the entire data, all the columns, right? But we are consciously moving more towards the columnar data set so that we decrease the read volume. But yeah, right now, like it's pretty high read volume compared to writes.
And then as far as you said mostly Cow, but can you comment on what your more cases are, merge on reads?
Yeah, so it's all Cow, and yeah, it's all Cow.
A little bit.
Yeah. But I think we do see a reason where merge and read can help out. These are essentially CDC use cases, but there is no production CDC use case powered by Iceberg at Pinterest right now.
Thank you.
Yeah.
Yeah, I have a question about your sorting. So why not just do partitioning, like have a table property there for partitioning or Z ordering? Because then overall you would benefit from that as opposed to do this trick with sorting.
Right. So they have their own pros and cons. The overall table partitioning, we do it like everyone else. We do the date and hourly level partitions. Partitioning by particular identifier is never a good idea. For example, user ID or advertiser ID. We can do bucketing. We looked into that, but then pre-Iceberg or even now, actually, I'm not sure about now the current state, but then the issue with bucketing is that your Spark bucket, like if you have a table bucketed by Spark, you can't read from Presto, vice versa. And for that reason, like for us, the interoperability was very important. And then bucketing has its own challenges. It could be that like you'll see a data skew, and then like that really hits your performance as well. The Z ordering is something we are excited about. We haven't played around with it. It wasn't added to Iceberg until I don't remember the exact version when they were added.
I think 1.1.
Yeah. So we are still at 1.0, and so yeah, we are excited about Z ordering. As I said, like the journey I shared was the journey we went through. It's not end of the journey. We will definitely be looking into more ways to optimize. Z ordering definitely will be one of the things we are excited about.